21. Write Lewis structures for NF3 and PF5. And then on the basis of hybrid orbitals, explain the fact that NF3, PF3, and PF5 are stable molecules, but NF5 does not exist. Okay. So the first thing we have to do is write these Lewis structures out. So maybe we will split this into two, and we will put, and I don't like that this, okay, beautiful. We'll put NF3 on the left, and I'm just being picky. That's fine for now. And then PF5, right? All right, so NF3, least electronegative, is always in the middle, right? Fluorine is the most electronegative element in this world, so nitrogen is going to be in the middle, surrounded by the 3 fluorines. Okay? Nitrogen is in group 15 or 5A, so it has 5 valence electrons, 1, 2, 3, 4, 5. And then fluorine is a halogen, that's 17 or group 7A, so it's got 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Always make your single bond first, so dot to dot, dot to dot, dot to dot, and then just check your outer elements to see if they have the octet. So this fluorine has 8 electrons, right? 2, 4, 6, 8, so that one's good. The same thing with this fluorine and this one. Now, since we have the all fluorines figured out, the nitrogen is also, it has the octet, right? 2, 4, 6, 8. So there's your first Lewis structure. Now, let's do the one for PF5. So in this case, you have phosphorus in the middle, surrounded by 5 fluorines. So 1, 2, 3, 4, 5. Phosphorus has 5 valence electrons, so 5 dots around the phosphorus, 1, 2, 3, 4, 5. And then each fluorine, once again, has 7, so 7 for that one, 7 for this one, 7 for this one, right? How's your day going? Mine's going pretty well. Doing videos for you guys. Love it. 1, 2, 3, 4, 5. Boop, boop. And one last one. 1, 2, 3, 4, 5, 6, 7. Okay. Single bond it up and see if those outer elements have the octet. But with halogens, once you make that single bond, they're always going to have the octet. So since fluorine has the single bond and the 3 lone pairs for each one of them, they all have the octet rule, so that's perfect. And phosphorus, even though it has 10 valence electrons, or not 10 valence, 10 electrons here, that's okay, because phosphorus can have access to the d orbitals. So now we're on to the second part. Based on the basis of hybrid orbitals, explain the fact why NF3, PF3, and PF5 are stable molecules, but NF5 does not exist. So, if we basically discuss what the hybridization of the nitrogen here and the phosphorus here are, that might give us a little indication of why NF5 does not exist. Now, hybridization comes down to just sp and d orbitals that come together to form the overlapping of your bonds. And the hybridization has everything to do with just as many letters as they have. So, for example, sp3 has 1s and 3 p orbitals, so that's a total of 4 letters. And the number of letters corresponds to the number of things. So, one single bond is one thing, one double bond is one thing, a triple bond is one thing, and a lone pair is one thing. So now when I go over to nitrogen and I say, how many things does this nitrogen have? Well, it's got a single bond, that's one thing. It's got another single bond, that's 2 things. It's got one more single bond, that's 3 things, and a lone pair. That's a total of 4 things. So 4 things, 4 letters. And the 4-letter one is sp3 hybridized. Okay, now let's see, is the phosphorus hybridization going to be the same? Well, what does phosphorus have going on around that one? Well, it's got a single bond, that's one thing. 2 things. 3 things. 4 things. 5 things. No lone pairs, so no more things. So 5 things, 5 letters. That's the sp3d hybridization. Okay. So we're getting somewhere. So now we have to say, why does NF3, PF3, and PF5, why are they stable, but the NF5 does not exist? Well, it seems like if we go by this and we try to eliminate the phosphorus and put a nitrogen here, nitrogen would have sp3d hybridization. So the question is, can a nitrogen have sp3d hybridization? Well, if we look at the electron configuration of nitrogen, right? Nitrogen has an electron configuration of 1s2, 2s2, 2p3. Now, the highest number that nitrogen has are 2. Your principal quantum number, the highest number for nitrogen is a 2. And if your highest number is a 2 for your principal quantum number, you only have access. Does access have 2 C's or 1 C? Let's see what it looks like with 1 C. I think it has 2 C's. So it only has access to S and P orbitals, because the D orbitals, you have access if your largest number is at least a 3. So if we look at the phosphorus electron configuration, and what phosphorus's electron configuration is, it's 1s2, 2s2, 2p6, 3s2, and 3p3. The highest number for phosphorus is now the principal quantum number of a 3. And if you have a 3, you have access to S's, P's, and D's. So that's why NF5 does not exist, because nitrogen only has access to S and P orbitals. If it was trying to make an NF5 Lewis structure, it would need to have access to the D's, because once you have 5 bonds, you need a D orbital. And since the quantum number only goes up to 2 for nitrogen, you don't have access to those D's. You can't have 10 electrons. You can only have a max of 8. So because of this also, you have a max of 8 electrons, not 10. Not an expanded octet. And that's what this has. An expanded octet is only for elements that have access to the d orbitals. And that's it. So the other ones, NF3, PF3, PF5, these would have your nitrogen as sp3 hybridized. They have access to S and P orbitals. PF3, that phosphorus would be also sp3 hybridized, and it's got access to S and P's. And this one was the sp3d because you have access. So there you go. What'd you think? Hopefully this helped. Let me know in the comments. Subscribe to the channel, and I look forward to helping you with more problems. We will produce more problems, and you just keep studying from them. All right? It's a win-win. I will see you later. Well, not really see you, but I'll talk to you later. All right? Have an awesome day. Bye-bye.